So was this problem on the mock competition?
No.
No.
This one I actually found UCF, one of the coaches, they have a list of questions.
Oh, okay.
This was one of them.
Okay.
I thought it was a good problem.
Okay. Does the problem make sense? All right.
When it says he cuts it across the cake, is it through the diameter? Or?
No, it doesn't have to be. Could be anywhere. Because the cuts are given as equations of a line.
Okay.
So they could be through anywhere. Okay. Any parts of the problem or the question that's not clear?
Like if there are n candles and the father wants to cut in such that each piece has one candle, and if it's successfully able to cut, then whatever the number of candles is there, the number of pieces are also there.
Exactly. So it'll be, I commit. So then the answer would be yes, otherwise it would be a no.
If a cake piece has two candles, like 5 candles and 4 pieces, so eventually if one piece got 2 candles, then it will be yes or?
Then it would be a no.
Okay.
Yeah. Is that clear?
Yeah.
Okay. So you're given the cake, you're given the cuts, you're given where the candles are. All you have to do is figure out yes or no.
If each slide will have one.
Correct. Okay. So that's the idea behind the problem. So let's look at the slides now and see if this starts to make sense. Okay. What is your name, miss?
Journey.
Jenny?
Journey.
Journey.
Yes.
Okay. Nice to have you here. Hey, Dimba. So we're going to talk about this birthday cake problem. I should put it on the.
I think the problem on Discord, we should see it.
Okay. All right. Oh, before I do that, the Southeast Regional Competition has been set for February 25th. So make sure it's on your calendar now, and make sure you're available at that time to compete with us. Yeah. Also, what we'll try and do is soon we'll try and form some teams, and then it's probably a good idea for you to start practicing with your team, so that you start to have some coordination within the team, and you can also within the team you can build different skill sets, so that as a team you'd be awesome. All right, that's the general plan. And the sooner you collect your team, the better it is. If you don't have a team, let us know. If you have somebody that you like to work with, that's fine. That also is okay. But if you don't, let me know so that we can start to plan on this as soon as possible. Okay? Everyone okay with this? Yeah? And remember, this competition happens here. It's essentially across the street in PG6. And it's an all-day affair. So don't plan on anything for that day, or for a few days prior to that, or for a few weeks prior to that. Yeah. What fun. All right, so we're going to talk about the birthday cake problem. Here is the link to the problem itself. my animation is out of whack. So what you're given is a cake, and you're told that the cake is a circular cake, and it has a radius of r. The number r is given to you, and you're given a set of straight line cuts. Straight lines are specified using. By the way, the center of this cake is the origin, and the cuts are given to you as equations of lines. Okay, so in this case, you're told that it's ax plus by plus c equals 0, and your a, b, and c are whatever they give to you. Okay, so once the line is specified, you know exactly where that cut is going to be. Then you're also told that the candle has a bunch of cakes. A cake has a bunch of candles, and you're told the positions of each of the candles. You're told how many candles and where they are all located. Okay, and then you're asked the simple question whether your set of cuts does the cut in such a way that each piece is a candle. And for this particular situation, the answer should be there's a piece at the bottom here, and there's a piece at the in the middle here that does not have a candle, and that is not acceptable either. So you can't have pieces with more than one candle. You can't have pieces with no candles. Okay, is that clear? So if these are the lines that are given to you, your answer should be no. Fine? By the way, it's possible to move these lines in such a way that the answer is yes. So for instance, I could move this line a little bit so that this piece goes away, and so if it were something like this, then you won't get this extra piece here without changing any of the other regions. And also you could move this in such a way that maybe, you could slide this line a little bit and make sure that all three lines pass through one point here. That way this little triangle would disappear as well. Okay, so it's possible to move these lines around in order to make this work. But that's not what you're asked. That's not your problem. Your problem is simply that you're given the lines and you're asked, does this work or not? Is that clear? Okay, so question is, what am I going to do? Before I do that, there are a few more details that's useful. It's always a good idea to know a little bit about these details. You're told that the number number of candles. The number of candles on the cake is less than 50, at most 50. You're told that the number of cuts is at most 15, okay, and the radius of the cake is at most 10. And all the points have integer coordinates, and all the lines have integer coefficients for them. Okay, these are just useful because as you go through the problem, these numbers will help you make some decisions about how to approach this problem. Okay, so question is, the center of the cake is at 0, 0. All the cuts are equations of a line. You remember this from your coordinate geometry days. And so every cut is some equation like this, ax plus by plus c equals 0. And you're also told that you never have the case where both a and b are 0, and all these coefficients a and b are at most 100, and finally the number c could be a bit larger. It can go up to 20,000. And these are useful to know because they have implications. Okay, much of this is to prevent you from picking algorithms that will not be very efficient. So that's the reason for some of this detail. So question is, how do I now solve the problem? And remember, the problem is you're given the cake, you're given the positions of the candles, you're given all the positions of the cuts, and you're asked a question, yes or no, does every piece have exactly one candle? Is that clear? Okay, so what should I be doing? Oh yeah, there's one more little piece of information. There's a precision of 10 to the power minus 4. Essentially, all that says, at least the way I understood it, their language is a little poor there, but the way I understood it, if you go up to 4 decimal places, that's enough. So, how would I approach this problem? What should I be doing?
Maybe try like one line and see, like use small numbers to start with.
Yeah. You want to keep the number of candles the same and try one line, or did you want to try number of candles also smaller? What is your what was the purpose of just trying one line?
I guess to see if you can like generalize it for more lines, some kind of intuition to get from one line.
Okay. All right. So what kind of information do you want to extract about having one cut, one line? It'll just cut some candles on this side, some candles on that side. How does that help you?
We need a way to detect the number of candles in a region.
Detect the number of candles in a region. Well, for that you have to detect the region. You have to figure out the region itself, right? So that means you have to kind of, if you go back to this picture here that I had, yeah, in this picture, you're saying I'd have to compute each of these regions and then figure out how many candles or which candles are in each of these regions, right?
Yeah, that would be.
That's the approach that comes to your mind first. All right. The problem there is it's very complicated because, first of all, even if this circle were not there, trying to figure out what those regions are does not look like a very friendly problem. On top of that, this circular cake makes things even worse because now I have regions that are bounded by this circle. So these regions are not even straight line polygonal regions. They're nasty looking regions with little curves and so on. So all that makes it very, very unfriendly, right?
If, like, let's say you just had one single line in the problem,
Yeah.
then you can tell if it's to the left, each candle, or to the right of that line.
Yeah, let me stop you right there.
Okay.
Yeah. Did anyone understand what he said?
Keeping track of what's in the left and what's in the right.
Yeah. So what do I do then?
Then we take left hand side or either right hand side, then
Uh-huh.
apply same method.
Sorry?
First cut from.
So for some line, I determine left and right, and I know points, candles that are on the left, candles that are on the right. Okay. Then
we choose other right side or left side and then apply same method.
apply the same method. But then a second cut would cut through both sides, so I can't just recursively solve the problem on the left and the right. Right? It's not a circular cake anymore on both sides. Yes, Demba.
What if like you do it for one line, right? And then do
Yeah.
it for another line and keep track of the.
So what if you start to add lines? That's what you're suggesting.
And then keep
Yeah.
doing the left and right thing, but keep track of like for each point, see how many lines it has on the left boundary and on the right boundary.
Uh-huh.
And then you use that information to somehow determine if it isn't.
Okay, let me stop you right there. Did anyone understand his complicated idea? Is it complicated? Maybe it's not so complicated. Anyone understand this? Would you like him to repeat? Yeah?
He's right.
He just continues to add more lines, and you have more left and right things, and then what?
He'll slowly see like what lines or what dots keep getting repeated, like near. Like he's gonna keep track of left and right, so we're gonna know the.
Sure. Will that help me though? Remember, the question I'm trying to answer is, let me draw that picture here on the board. What I'm trying to figure out is, I have something like this, and I know my cake, and now I just need to figure out whether every region that shows up here has a candle on it, right? So the first idea was you take one of the lines, let's say that one there, and then you go, this is left and this is right. Something like that. And then what?
And you do it again. So you take the left side, you divide it.
Yeah, so you're saying pick another line here and do a left and right? On either side, I see. So you're saying take this second line and just work with the piece over here and do left and right, something like that.
That's how I interpreted it. Yeah.
That's how you interpreted it. Okay. He said something a little bit more, but let's go back to what I'm trying to say in the slide, which actually is pretty much following his idea. You need to start with this question of which side of any line you are. So take any line, like we picked this guy here. Every candle is either to its left or to its right, right? That much is fine. And you can figure out which candle is to the left and which candle is to the right. And you can actually do this, you can do this in coordinate geometry. Let me try and explain this to you a little bit more. Imagine that you have a line. In this case, the line is given as y equals mx plus b, but it's no different from ax plus by plus c equals 0, right? Now, if that's the line you're looking at, and remember the equation of the line is y equals mx plus b. Now, it turns out that this line divides the entire plane into two half planes, where on one side you're going to get y is strictly less than mx plus b, and on the other side you're going to get strictly y greater than mx plus b. Okay, and that's how these line equations happen. Same thing, in this case the equation was y equals mx plus b, but I could equally well have had ax plus by plus c equals 0. If my equation is this, then on one side you will have strictly greater than 0, on the other side you'll have strictly less than 0. Okay? This is how coordinate geometry works. For any point, if you take the coordinates of this particular point, it has a certain x value, it has a certain y value. If you plug it into the equation for this line, what you'll find is that the y value for this point is strictly less than m times the x value plus b. Okay? And this is going to be true for this point here, that point there, that point there, that point there, because it's all in the gray area. On the other hand, if I take any point over here, it's going to satisfy the inequality that y is strictly greater than mx plus b. You can put it in this form. If the equation of the line is ax plus by plus c equals 0, on one side I'm going to get greater than 0. On the other side I'm going to get ax plus by plus c strictly less than 0. All right? So we know that this is going to happen to each of the cuts, each of the lines. So the question is, how is that going to help me? And this is where we have to use the ideas that they were suggesting earlier on. Does this make any sense to you? What's next? What do I do? Any thoughts on this? Let me see, what do I have on the... So one way to approach this is, it doesn't matter how I label them, but one side I'm going to label as the plus side of the line, and the other I'm going to label as minus side of the line. I could have equally well have labeled it left and right, or anything else that I liked. As long as the labels are different, I'm just going to label the regions, which means that any point on this side is on the plus side of this line, and any point on this side is on the minus side of this line. Typically, there is actually an easy way to figure this out, or to assign these labels. You can just take the origin and plug it into the equation of the line, okay? And then you'll find that the origin has x equals 0, y equals 0, right? So if you plug it in, the left-hand side becomes 0, the right-hand side becomes m times x also becomes 0 because x is 0, and then you only get b on the right-hand side. So if b is positive, then y is going to be less than b for a point over here, whereas if b is negative, for the point here, you're going to get y to be bigger than b, right? So essentially, you can label things as saying this side of the line is everything that includes the origin. I'm just going to arbitrarily label it as plus. And this side of the line is everything that doesn't include the origin. Okay? So this is just a simple way to label it. If you want, there are other ways to label it as well, but it's completely arbitrary at this point. I'm just going to call one side as plus and the other side as minus. And that's because every line breaks the plane into two half planes, and I'm just arbitrarily labeling one as plus and one as minus. Is that clear? So it turns out that this is where the next idea comes up, and this is similar to what both these guys were suggesting, and that is I will get a plus and minus label for every line that I have. So every cut will have its own left side and its own right side, or its own plus side and a minus side. Does that help me? Don't see it?
You can find out how many cuts are there.
How many cuts? Well, how many cuts you know that already. I know that there are m cuts, right? That's part of the input to the problem. So for each cut, I even know the equation of the line. So that means I know exactly the plus side and the minus side for each of the lines, right? So every line, there's a definition of plus and minus that I've used, and I've labeled it appropriately. Now here is the key point. We know that there are m lines, right, or m cuts. We know that each candle is on one side of the line, right? So therefore, I'm going to label it that way. I'm going to label one side as plus and the other side as minus, which means every candle will now get m different labels, one for each of the lines, each of the cuts, right? So for this cut, I'll get a label. So imagine that I have a candle somewhere. Let's say I'm looking at the candle right here. Okay? And for each of the lines, I'm going to provide a label. So I'm going to say this is L, this is R, this is L, this is R, this is L, this is R, this is L, this is R. this is L, this is R, and then L and R, L and R, and L and R. Oh, one more, L and R. Okay? I've arbitrarily labeled one side as L and one side as R. I'm going to just take R as plus and L as minus because I used plus and minus on the previous slide. So that means, and I'm going to number the cuts. I'm going to call this cut 1, cut 2, cut 3, cut 4, cut 5, 6, 7, 8, 9, and 10. Okay? So there are 10 cuts. Oh, I'm sorry. Actually, I'm counting them twice. I only need it on one side. And you have one?
Yes.
Amazing. Okay, thank you. I don't need on both sides, so I need 1, 2, 3, 4, 5. This is simply the same as 1. That's simply same as 2. All right, I can erase these. So there are 5 cuts, right? Actually, these are all confusing, so I'm going to remove that. So there are only 5 cuts here, right? And for each cut, I have a right side and a left side. And I've also labeled the cuts as 1, 2, 3, 4, 5. So now, if I take any candle, right? This candle will have a specific will have a specific property. It says that it's on the, if I look at 1, it's on the right side of 1, so I'm going to call it a plus. It's on the right side of 2, so I'm going to call that a plus. For 3, it's also on the right side, so I'm going to call it a plus. It's on the left side of 4, so I'm going to call that a minus. And it's on the right side of 5, so that's a plus. So that means this candle will get the following labels. Is that clear? So therefore, every candle, I will assign labels like this. How is that going to help me?
You could see, like if each is like an equation, then you know that the negative of one is not being used. Like there's nothing there.
Right. Well, you have to see something more than that. So for instance, if I consider any point in this entire region, all right, it doesn't matter. In this case, the candle is right here. I could have moved it here or here. All those candles will have exactly the same labels. Right? So therefore, in any given region, the labels are going to be they're going to be identical. You agree with me? You see that? So therefore, if I can label each of the candles, what am I checking? If they have the same labels, right? The same signs. And if they do, then
they violate.
then they violate the, then you have more than one candle with the same label. So we have an easy way to check if any region has more than one candle. We're left with checking whether any region has no candles. You have a question? That was the second question. Okay. All right. I'm going to ask you that question back. I'm going to throw that back at you. How do I check if a region does not have a candle in it? This one is a little more difficult. So we'll tackle this. Give me a few more minutes before we tackle this. Okay, it's not a straightforward answer, but at least the easy case. Let's take care of it here. This says we have m lines. We can label each candle according to that line as either plus or minus, right? Meaning, is it on the plus side of that line, of the first line? Is it on the minus side of that first line? Then we'll look at line 2. Is it on the plus side or the minus side of line 2? We'll do that for each of the lines. And then we'll get a vector of labels, right? Like this. So it's on the plus side of line 1, plus side of line 2, plus side of line 3, minus side of line 4, and plus side of line 5. And now, as he said, all you have to check is whether there are two candles with exactly the same labels. If it has exactly the same labels, then what we showed was that it must sit in the same region, and that means that you would have more than one candle. By the way, how do I check whether two candles have the same set of labels? What should I do?
Hash.
Sorry?
Hash.
Hash, yeah. Think of hash as the last resort.
Maybe plus is 1, minus is 0, so it's just a number.
It's just a number, and then?
Just check. You can have an array, and then just check it.
Then you can just sort it. Okay, if you take all the vector of labels, and if you sort it, then after that, what do you do? Yeah, you just have to run through the list, and your duplicates will be next to each other, right? So I get a whole bunch of labels. They're all going to look like this. I am going to simply sort it as if this were a string, right? Or if you want to take numbers, you can take numbers. That also is fine. And then check whether any adjacent ones in that sorted order are identical. Easy. By the way, how do I sort something like this? What kind of sorting algorithm? My algorithm students here?
Counting sort.
Counting sort. What kind of algorithm would you use? What kind of sorting algorithm would you use?
Radix sort.
Sorry? Radix sort. Very good. Yeah.
Radix sort.
So there's something called radix sort where, or you can use counting sort. That counting sort should also work. Yeah. Yeah. Yeah.
What if you store it in like a Boolean array? Then you wouldn't need to sort it, right? And then maybe true might be positive.
Yeah, same thing. Yeah, but either way, you're going to need to know whether two of these are identical. The Boolean array doesn't really help. The sorting is what will help you.
The radix sort needs a stable property to be basically.
Yeah, so you just have to decide that minus is less than plus, for instance, and then you'll be done. Okay. As long as you have identical labels, sequence of labels, you'll see them next to each other. That's all that matters, right? Okay, so we've taken care of most pieces except for the problem where there's a piece with no candles, right? How do we detect if there is a piece hanging out here with no candles? Yes?
I think you have an error in the slide with the second when the vectors and labels are identical. It should be
Yeah, that's right. Yeah, this should be, if they're in the same piece, they're going to be identical. If they are in different pieces, they are not identical. Yeah, you're right. Sorry. Yeah, yeah, this should be not identical. Okay. I don't have the part written up for the next piece. Well, but here is the basic algorithm for the first case. Okay. So for each candle, for each label, for each line or each cut, figure out the assignment of labels, then sort the labels, and then check if if two of these are identical of the ones that are sitting next to each other. What is the time complexity of this? What is the time complexity of the first for loop there? How many candles? There were n candles. There were m cuts. And that's it, actually. So for each candle and for each cut, I have to figure out a label. How much time will that take me?
N times n.
M times n, right? So the first two for loops, that's going to take me order m times n. That's good. So, and then in order to sort, if I'm going to use counting sort or radix sort or bucket sort or any of those sorts, it's again going to take me, actually it'll take me,
Each candle, right?
yeah. So it's actually n plus n. Although I think I may have written this wrong. It's not n times m, it's n plus n. So it uses something called a lexicograph. You could also use something called a lexicographic sort. There are many ways to do this. If you use standard lexicographic sort, it'll be n times m. If you use a radix sort or a counting sort or a bucket sort, it'll be n plus n. So you could make this better, but it doesn't matter. Still, this is the dominant cost. So all of this is pretty clear. So you're left with trying to figure out how, whether there are any regions here with no candles. We've made sure that there are no regions with two candles, right? So one approach might be, well, let me allow you to think about this. Yeah.
You were able to somehow count the number of pieces you
Right.
compared to.
Yeah, if you can figure out how many pieces there are, you know how many candles there are, and all you have to do is match these, right? If they are exactly a match, then you're great because you already made sure that there is no piece with two candles, right? So there won't be a piece with 0 candles. You'll be fine. But if they are not the same, then for sure you'll have a problem. So how can I do counting of the cuts of the pieces?
Not fully thought out yet, but since the number of cuts is very small,
Yeah.
let's try to brute force every left, right,
Uh-huh.
and sort of check if this region is inside the circle.
That's right. Yeah. So generally, here is a possible plan based on what Ricky just said. Let me explain what he was trying to say. He was saying that if you take any two cuts, well, for sure they will intersect, unless they are parallel. No, I guess parallel cuts are allowed here. So we have to be a little bit careful. So I can take any two cuts and I can decide whether they are parallel or they're going to intersect. Okay? So assume that they are not parallel, and that's easy to check. If they are not parallel, they will intersect somewhere. However, the problem is that unless this intersection happens within the cake, right, you are not going to see all possible cases. If your cake includes this point of intersection, like so, then you will get all 4 possibilities. Otherwise, if it sits over here, you're going to see only 3. If it doesn't intersect that other line, you'll see only 1. Or if it intersects neither line, you'll see a 0. So for every pair of lines, one of these cases must happen. Is that clear? And each of these will set up something for you. In reality, that's not how you would do it, but I'm trying to build some intuition for you. Okay? Is this helping you at all? Not really, no? Okay, so let's think about this as a little differently then. What we're going to do is, right. We will count, we can count the number of regions that are formed by, you called it brute force, but actually that is not brute force in this case, because you do have to go to each of the regions anyways, right? So here's how I'm going to, right. Let me erase this and restart this picture for you. Can I erase this? Is that okay? Okay, so first of all, let's start with the cake. Here's the cake, right? Let's ignore the candles for now, because the candles we're not concerned anymore. All we care about is how many cuts, how many pieces of the cake are going to be produced. That's all we care about at this point, because if that equals the number of candles, we're all done, right? Remember this? Okay, so I'm going to start with the cake. At this point, how many pieces are there? Just one, because we haven't cut anything. Well, if any of the cuts are totally outside this cake, again, it's not going to add to the, I can throw that out right away. It's not going to affect anything, right? Is that clear? Okay, so let's assume that all the cuts we have that are remaining, they all cut the cake somewhere. Fine? So what I'm going to do is I'm going to pick one of the cuts and I'm going to follow it. So now I know it enters here and it leaves there. So immediately I get two regions. So I'm going to keep track of this. So my current count of as long as this first cut cuts the cake, I'm going to get two regions. Fine? Now let's try the next cut and see what happens. So I start the next cut, and let's say that next cut goes like so. Okay? So I'm going to enter this cake somewhere, right? And I figure out whether this point here is in region 1 or region 2. Okay. By the way, when I did my first cut, I'm actually going to build these regions. I am going to build them like so. Okay. I'm going to follow that boundary and keep track of it. Okay. And the second one also, I would know this guy here. The boundary is here, and then it goes around and comes like that. So that's my region 1 and region 2. The boundaries of these regions now are either straight lines or they're part of the big circle, of the circle that forms the cake. All that is fine. Now when I start the second one, I'm going to figure out where it cuts the cake, and then I know since it's on region 1, I know that region 1 is going to get split into 2. Okay, so I can increase this number to 3, and all I have to do is to figure out where it exits this region 1. And so I will go through the entire boundary of 1, figure out where it exits. So that's how I get this point here. All right, and then at this time I know that it's going to touch. It's going to cut into region 2, which means region 2 will get split into 2 parts. That means I can increase this to 4. Fine? So therefore, then when I do that, I'm also going to update the regions, because this region now is going to be, it's going to be something like this. It's going to go like so, like so, like so. So I have all of this as one region and all of this as second region. So one has become 2 regions, and the boundaries of those regions are also updated. And they will only get updated by the piece over here. In general, as we go along, as we continue this, you'll see what happens is that if I start a new line, a new cut, let's say that this cut goes through like so. Okay? It'll enter somewhere. It enters this region 2. Region 2 again gets cut and will get broken into 2 pieces. One piece will look like this and like this, and then it will exit region 2. Then it will enter whatever this region is, and that region will get cut into 2 pieces. One will look like this and one will look like this. And then it'll exit it over here, and then it'll enter a new region, and all that will keep continuing until it reaches the curved region of the cake, and at that point it'll go out. So at any given time, I'm going to have all the regions that are produced by the cuts and also their boundaries. All right? And more importantly, it's going to look like this. I am going to have every region is going to look like this. It's going to have a bunch of straight lines and then maybe a curved part. Okay? So it's going to be some piece of the cake which was formed by various cuts, and that's what a slice is going to look like. So I'm going to actually keep track of the slice itself. All right? Now think of what happens in the future. When I add an extra line, and if that line does cut this slice, it must enter at either one of these straight line pieces coming from somewhere here, or it must come in from outside the circle cutting the cake for the first time. Okay, so we can take both cases. So let's say it gets in here. The moment we figure out where it is on the circular arc, I know that it's going to cut this region, because any cut has to cut right through, right? All cuts go all the way from one end of the cake to the other. So therefore, this is going to cut all the way across, and the region that I have, imagine that it's a linked list. What I'm going to do is to follow this linked list all the way to the other end, and then I'm going to cut it short and then break it into 2 such pieces. And now I'm going to have something that looks like this, and the other one is going to look like this. So I ended up taking this slice and making 2 slices out of it. And I would have to keep track of this in order to figure out that I've created another region. And every time I cut, I break one region into 2. Yeah?
Kind of following this idea, I'm just kind of working it out.
Yeah.
Won't it be the number of intersections that are
It is. That is inside the circle. That's correct. So you could, yeah, I should have said this earlier. There are actually a gazillion ways to solve this problem, and you can decide which one turns out to be easier. This general version is useful for solving many more geometry problems, and that's why I'm giving you this approach. and the time complexity is going to be essentially the number of regions and the number of faces on each of these regions. So it's not horrendously large time complexity. But the other approach, we can actually talk about that. That may be easier for everyone. So maybe I'll
Just out of curiosity, is it possible to use this algorithm if you're not guaranteed that all the lines cut completely through the circle?
This algorithm you can, but other algorithms maybe not. Because this algorithm, let's say the cut stops here, then what will happen is that this piece here will wind around in strange ways. Okay? But then the search for where you enter the cut becomes way more complicated, and you have to keep. There's a lot more bookkeeping to take care of. Okay, so Ricky just provided another idea which may be simpler for some of you. So let me go through that. His idea is take every pair of cuts. Okay, find its point of intersection, and then check whether it's inside the circle. Okay, so that way you can count the number of intersections inside the circle, but that still won't tell you how many regions, does it? Oh, because there's a formula for Euler's formula. So if you find the number of intersections inside the circle, in this case there are 3, 1, 2, and 3. As you add more cuts, there will be more intersections, and some may be very less. So here there may be only one extra cut, one extra point of intersection. Sorry, you also have to count these guys as well. So you count all the points of intersection with the cake and with each other, and then once you get the number, you can count the number of faces, because there's a formula that connects the number of edges, the number of points, and the number of faces. I don't remember the formula, but it does exist. So that's another approach that's slightly simpler. And once you know the number of faces, then we know the rest of the problem, right? This here is a much more general approach that works even if you don't have this circle and you just have an arrangement of lines. And if the number of cuts is very large, then the approach that I just gave you may be a little bit better.
What was the name of this approach? Does it have a?
This is called the arrangement of lines, or arrangement of half planes. Yeah, this whole thing is called a line arrangement, because you have a bunch of lines and you're looking at this entire region. And computing the line arrangements, there are efficient ways to do it. You can even find code for this. There's a divide and conquer method that's fabulous, but it can be a bit complicated. But one of the tricks here, one of the key things, if you're really going to implement this approach, is to take each of the faces and build what's called as a doubly connected linked list. And then, so this face will have one linked list, this face will have one linked list, and you will also have additional pointers that says these two guys share that edge. That way you can jump from one to the other very quickly. So I think there's another special name for it. It's called doubly connected something. I can't remember off the top of my head. But right. Let me show you how this works out for if you don't have the cake and if you just have lines. You will have a similar deal. You start with one line, okay, and here I have two regions, and I'm going to represent the region in this strange way where it goes to infinity here, and then the infinity connects back. All right? And so you have one above and one below. All right, so this here is the, think of that as the infinity, or think of this as the globe, and it's connecting on the other side. Yeah. So this is how you kind of get started, and then you add the second line. When you add the second line, you'll see that it enters from infinity somewhere, and we'll cut this in over here in one place, but actually the region gets cut in two more places. And so now you just have to chop this piece over here and build extra regions. And now I will have 4 regions, one that goes like this, one that goes like this, and then the blue ones also get broken into 2. Okay. Because we have the cake and the circle, that adds these regions are not infinite, and so you deal with bounded pieces. So in some sense it's easier here, but there is a general algorithm for if you don't have this cake. So when you do this part, I just showed you how to add 3 lines here. If you add the 4th line, then for instance, when this line comes in, it's going to chop up this piece into 2 pieces. So one piece is going to go like so over here. The other piece is going to go over here. And then when it crosses over to that region, that piece also gets broken into 2. And so each time you increment the count, so you're automatically keeping track of how many regions are formed. Then the moment it hits the end of the cake, you know that it's not going to produce anymore, and you can stop that. So you start where it enters the cake, and you stop when it exits the cake. And along the way, all the lines that it hits, each one produces 1 extra slice, because an existing slice gets cut into 2, so 1 gets replaced by 2. So the number of intersections gives you exactly 1 extra cut for this thing. So therefore, the earlier algorithm that Ricky was suggesting may be a little bit easier, where you try every possible pair of line segments and count how many of those intersections lie within the cake. And you know that when you're dealing with that cut, all those intersections are going to come into play, and they will all add one intersection for you. All right. So algorithmically, let me explain how this will look, or at least Ricky's easier version will look. I'm going to do the following. I am going to do for I equals 1 to m. Remember, I'm going through all the cuts. I won't do 1. Let me just start with 2. I am going to check if cut I intersects. I need another for loop here. So I'm going to go for j equals 1 to I minus 1. Okay. So essentially for every possible pair, I want to check if they intersect. So I'm going to check if cut I intersects cut j inside the cake. This is what we're checking for, right? If that happens, then I'm going to get 1. I'm going to increment the number of intersections by 1, and that intersection will actually chop. How does it go? So it will add one more slice to the whole count. Of course, it actually does it on both sides, but then this one will get counted later on when you exit it. So I'm going to increment the number of slices. I have to initialize the number of slices to. I'm going to initialize it to 1 because, remember, I'm only starting from I equals 2. So the first one, sorry, I have to initialize it to 2. Yeah. Actually, I also, it doesn't take into account what happens to the cake. If it happens, well, it's going to be, this number depends on whether that first cut intersects this cake or not. So it's going to be 2 if cut 1 intersects the cake. Otherwise, it's 0. Sorry, otherwise it's 1. All right, I know it's a bit messy here. Bear with me. So this is the first part, first step. It says you have to initialize this whole thing somehow. I'm going to initialize it with the first cut. If the first cut cuts the cake somewhere, then I will have 2 slices to start with. Otherwise, I will only have 1 slice, which is the whole cake. Right? And then I'm going to take the second cut, third cut, fourth cut. I'm going to look at all the cuts. For each of the later cuts, I check whether it intersects with one of the previous cuts, and if that intersection is inside the cake. If it is inside the cake, it's going to add 1 more slice to your cut. For every intersection, it'll add 1 more cut, 1 more slice. And as you do that, here you can report the number of slices. And if that slices matches with the number of candles, you're all set. Is that clear?
Yeah.
So if number of slices equals number of candles is n, then we're all good. Okay, then what should be the answer? Then you're going to report as?
Yes.
Yes.
Then you report as yes. Yeah. Otherwise, it's a no. By the way, this is all after you've verified that none of the regions has 2 candles, right? And that we already talked about.
What happens if one of the cuts, suppose the cake is already cut into 2 slices, and the second cut is not intersecting both the slices, but only 1 slice?
A good question, but it can't happen because all cuts are defined by infinite lines. So it has to go, if it cuts the cake, it has to cut it all the way through. You can't have a cut that comes in and just stops dead here. That's not a cut.
What happens if the second cut is
Yeah.
parallel to?
Yeah, if it's parallel to that, that's fine. If it comes in here, then it'll cut that one, right? Then it'll hit it here, it'll cut that one. Then it'll hit it here, it'll cut that one, and then it'll hit it here. And this one actually was outside this circle, so it's not going to be counted. And that's it, it stopped right there. So you can't stop it midway, but if it goes all the way, it is going to hit all the lines. It's just that how many of these lines does it hit within the circle? That's the key. And each one adds 1 extra slice to your count. Over here, it added 1 because it cut that 1 slice into 2. Over here, it cut that slice into 2. Over here, it cut that slice into 2. So each one added 1 more. And so it's the same as counting the number of intersections. So since there were 2 intersections, I have to make sure that I add 3. Yeah, I don't know if that did I get that right here? Yeah, I have to add an extra 1 here. This doesn't look right. Yeah. So yeah. So I need a +1 somewhere. Is that clear? Did everyone understand why you need the +1? Because you also have to deal with the cake. So the +1 happens only if it cuts the cake at all. If it doesn't cut the cake, you won't even get that +1. If it intersects the circle somewhere, you add a 1, and then you'd go through this for loop. Otherwise, you ignore it and move on to the next. So I need an if statement here that says if cut I intersects the circle, add 1 to the count, and then go through this.
For intersecting the circle 1, and then for
Yeah. If cut I intersects cake, then number of slices is to be incremented. Okay, so that takes care of this +1, and that's all I need. The rest is all correct. Are we good? Okay, so this was easier. I know this was a little complicated, but if you actually want to figure out what the regions look like, you can do that over here. Okay. Any other questions?
The suggestion that you were for the arrangement of lines.
Yeah.
So in that case, how actually we are going to track the regions? Is it going to be we are going to track the coordinates of the
Yeah.
intersections?
Yeah, every intersection coordinate will be a vertex, and each region will be essentially a polygon, but with maybe one curved side.
One arc, yeah.
Yeah.
One.
Well, it could have 2 curved sides actually, because if the cut goes like that, you could have 1 over here and 1 over here, right? So yeah, there are lots of weird cases that can happen. Yeah. We also did not talk about the case when more than one line, more than one cut goes through the same point. And that's actually a weird case. It really messes things up. The arrangement of lines algorithm does not like such cases. They usually assume that this does not happen. So if you're using some code, you would have to be careful. See if they are making that assumption. If they are making that assumption, then you would have to do something about it. And
What is the name of that algorithm that
arrangement of lines. It's called the arrangement of lines. Line arrangement.
the formula that
Oh, Euler's formula. Yeah. So yeah, there was one other piece that we did not talk about, and that is called the Euler's formula. Euler's formula is quite amazing. Euler was this amazing Swiss mathematician who figured out lots of crazy things from all over the place. But one of the things he figured out was that if you have, how does that go? If you have so just imagine like this. You have a bunch of lines, right?
F plus B equals equals to.
Something like that. What is that?
F plus B equals equals to.
Okay.
Basis plus vertices equal to edges plus.
Yeah. So this was Euler's formula, but then I was trying to draw a picture that illustrates it. Yeah. So let's do something fairly simple so that we don't get. Yeah. Okay. So let's say we have something like this. Here there are vertices. These intersection points are called vertices. Okay. Then you have something called edges. Edges are segments that connect the vertices. So in this case, by the way, how many vertices here? 4, 3, 7, and 3, 10. So number of vertices is 10. So V equals 10. Then there are edges and there are faces. So let's count the faces. So there are each of these regions that are formed are called faces. So I have 1, 2, 3, 4, 5, 6. 6 are all inside. Then there are outside faces as well. So I would have 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there are 16 faces. So F is 16. F is the number of faces. And finally, you're left with counting the number of edges. And the edges are basically these pieces here. Anything that connects two vertices, or anything that goes off to infinity. Now, counting those edges could be a real pain. So let's start with the infinite ones. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 infinity edges. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I think there are 15 edges that are not infinity edges, making it a total of 25. So E is 25. And something doesn't look right. I must have not counted right. Let me do this again. Well, I got pretty close, right? 10 plus 16 is 25 plus 2. I'm off by 1. Your formula is right?
Yeah.
Okay. Okay.
Not my formula, Euler's formula.
Did I miss something?
14 and 15.
Yeah, so all right, let me count again. Let me do the infinite once again. Is that 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that part is right. Then the other should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I'm getting only 15.
Maybe your words.
Sorry?
Your vertices are right.
Did I miss any vertices? That's a good question. It's possible that something meets something else later on. Is that possible? No, I think I got everything.
Faces and vertices are right.
Sorry?
They are.
No, it's only 14.
Sorry?
It's 14.
14? 14 you mean?
Yeah,
Yeah.
1 4.
Which one? Number of edges?
Mhm.
You counted?
Yes.
Okay. Let me count differently. So you have 3 here. Then 3 here, 6. 6 and 3, 9. 9 and 2, 11. 12. 12 and 3, 15. What did I do wrong?
14 should be more than 14.
Sorry? So there are 5 lines. 5 choose 2 is what? 5 times 4 divided by 2. So that's 10. So this number is correct. There are 10 vertices. Every pair of lines should intersect unless they are parallel, and there are no parallel lines here. So that one is correct. Is 16 correct? Maybe we do that again. Did I miss any regions? 1, 2, 3, 4, 5, 6.
I think we are missing edges.
Sorry?
I think we are missing one.
You think I'm missing an edge. Okay, let's do that. So that's edge 1. Well, let me start from the outer one. 2, 3. Let me only count the internal ones, right? The outer ones are 10, that's correct, right? Because there are 5 edges, so that must be 10. That part is correct. So let me go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. What did I do wrong? Sorry?
Should draw it again. A bigger one so you can actually see.
Okay, fine, I can do that. How am I doing on time?
It's 51, 4:51.
Oh, really? So I'm already past time. Homework, yeah. Anyways, if we had counted right, and if all the pieces fall together, essentially you can compute the number of intersections. Okay, and in this case, the intersection, some of these lines are going to be curved. Fortunately, Euler's formula applies there also, and so it's just a matter of trying to figure out what that number is going to be. And so you will essentially get the number of faces. But then you don't know either faces or vertices. So how are we going to do this? You'll only get by doing your count, we'll only get the number of vertices. We don't get the number of edges or the number of faces. So how are we going to solve this for number of faces? There's still some hitch there.
I was just working it out, added like intersections minus 1. That's the number of addings.
Yeah.
I thought Euler's formula was like for a 3D shape, so does it have to do with the fact that it's like on a plane? And we have lines going to infinity?
Euler's formula works perfectly fine on the plane. Let me check what's going wrong here. Something is going wrong. I'm not sure what. The number of edges is 16. I see. Look, each line is going to be cut by 4 other lines, so it should give you 5 pieces. And so 5 times 5 should give you 25. And that's exactly what I got. So 25 is correct. Because any line, now there are 4 others, they'll chop them, and you'll get 4, so you'll get 5 pieces, and that's going to be true on all the lines. So 5 times 5 is 25. This part is correct. This number of faces is the one that we should be challenging. Did we miss anything?
Counted all of the infinite faces? The ones that are
You can
facing?
check. You should check. I'm not suggesting that I did. Sorry?
I checked it.
You checked it? Annoying. I don't know what's wrong. Somewhere it's off.